All right, in this module, we're going to talk about hypothesis testing. And what we do in hypothesis testing is we want to learn something about a population parameter, for example, population mean. And in order to do that, we go into that population, take a sample, from that sample, calculate the sample mean, which is known as the sample statistic, and based on that sample mean, we either try to prove or disprove something that we believe to be true about the population mean. So why sample the population? Why not look at the entire population? Well, here's some reasons. Oftentimes the populations are large, so it takes too much time, costs too much, not be possible. And in other cases, the tests are destructive. And if you sampled the entire population, you would have nothing left of the population. It would all be gone. For example, if you wanted to know how long a particular brand of tire might last, you would take a few of those tires, you would put them on a car, you'd run them until they wore out, you'd figure out how long they lasted, and you would use that, the life of that sample of tires, as some estimate of what the entire population of tires life might be. But another big reason is we don't need to sample the population is because oftentimes sample results are just enough. Especially for reasonably sized samples, we get more than enough information. We don't need to sample the entire population. So in this module, we're going to learn about sampling, something called the sampling distribution of the sample means, the central limit theorem, and then we're going to talk about hypothesis testing. Now those first three topics are critical to the understanding of hypothesis testing, and so that's what we're going to talk about first. We're going to look at sampling, the sampling distribution of the means, then we're going to look at the central limit theorem, and then we'll get into a conversation about hypothesis testing. So what's a probability sample? Well, that's a sample such that every item in the sample has the same likelihood of being included in the sample. If you don't take a random sample, if every item doesn't have the same opportunity to be involved in the sample, then you don't have a random sample, and you cannot do hypothesis testing. You can't do statistical analysis of that data. So we have to have a random sample. All right, let's look at the second topic in this discussion, and that's the topic of sampling error. Sampling error is the difference between a sample statistic, for example, the mean, sample mean, and its corresponding population parameter, the population mean. So we see some of them over here, and we would expect that sampling error to be small. If we go into a population and take a sample and calculate the sample mean, we know that every time we do that the sample mean is not going to be exactly equal to the population mean, but we want it to be close. And large differences, large sampling errors are unlikely. And the fact that large sampling errors are unlikely is the basis for hypothesis testing. Okay, sampling distribution and sample mean, really important topic. The sampling distribution of the sample mean is a probability distribution consisting of all possible sample means of a given size selected from a population. So let's see what that means. Let me see if I can explain that to you a little bit. Here I have a population. This population consists of 7 items. We have 7 employees, and we have the average hourly wages of those 7 employees. If we were to go in to that population and take samples of size 2, we could get a number of those. So for example, we could get Joe and Sam. And that sample mean would be 7 plus 7 divided by 2 is 7. We could get Joe and Sue, and that sample mean would be 7.5, and so under many others. So what we want to talk about is this distribution called the sampling distribution of the means. So let's and what we want to know about that is what's the mean of that sampling distribution of sample means, and what can we say about how that relates to the different population parameters? And we're going to talk about that next. The standard error of the mean is a measure of the variation in the distribution of the sample means. I know that's probably hard for you to think about what I'm talking about now, but I'm going to get to an example in just a minute, so I think you'll understand what I'm talking about. But the key points here are two. One is that the mean of the distribution of sample means will always be exactly equal to the population mean if we select all possible samples of the same size from that population. We have to take them all. The second point is that there will be less dispersion. In other words, the standard deviation will be smaller in the sampling distribution of the sample means than it is in the population. And in fact, this standard deviation gets smaller and smaller as the sample size increases. And that should be obvious from the definition up here. The population standard deviation is fixed. It's a constant. So as n gets bigger and bigger, the standard deviation of the x bar has to get smaller and smaller. All right, one more thing. It's called a finite population correction factor. And if we take our sample from a finite population rather than a very, very large or infinite population, we have to make an adjustment in the calculation of the standard error of the mean, or also known as the standard deviation of the sampling distribution of x bars. And here is the adjustment that we have to make. We have to multiply by the square root of this capital N, which is the population size. In the case that we just looked at a minute ago would be 7. The little n is the sample size, which would be 2 in that case. So this is the population finite population correction factor, and for small populations, for finite populations, we have to use this. Okay, so what you're looking at now is these are the 7 employees that we looked at just a minute ago, and these are their wages. So I've got that listed here. This is the population. And from that population, we're going to take samples of size 2. It turns out that there are 21 different samples of size 2 that we can take. And we've got them listed here. Joe and Sam, Joe and Jan, Sam and Jan, Joe and Sue, and so on. And these are the sample means from each of those samples of size 2. And this entire collection of all 21 of these sample means, that is what is known as the sampling distribution of the sample means. So it in fact is also a distribution. Just like this population has a distribution, the distribution of sample means also has a particular distribution. What we talked about just a minute ago was that if we take the average, which we will right here, if we take the average of the wages of those 7 employees, that should be exactly the same as if we take the average of all of the sample means of size 2. And it turns out it is. If you look at that, you'll see that we have a 7.71 here and a 7.71 up here. Now, the other point that we made just a few minutes ago was that the standard deviation of the distribution of sample means should be smaller than the population standard deviation. And if we look here, if we calculate the population standard deviation, and I did this, by the way, using the formula function up here, and going into the formula function, let me just show you that. If you go to formulas, you go to more functions, you go to statistical, and you can scroll down, and we'll find down here in the S's, we'll find the standard deviation. We got one standard deviation for the population and one to calculate the standard deviation of a sample. But I used the one for population here. So we actually determined that the standard deviation of this population was 0.699, almost 0.70. Now the sampling distribution of sample means is also a population, so I used the same formula. I used the standard deviation for a population to get that number, and it turned out to be 0.4517. And as we expected, it's smaller than the standard deviation of the population. So the standard error of the mean, which is the standard deviation of this distribution of sample means here, is smaller than the standard deviation of the population. And in fact, I told you just a few minutes ago, what that relationship was like. Since this is a finite population, I used this formula right here to do the calculation, and we illustrated that if we use that formula, we can actually see the relationship between the standard deviation of the population and the standard deviation of the sample means. Now the final thing I want to show you is something that I'm going to get to in just a second. I want you to notice the shape. If I do a bar chart of the population, it looks like this. But if I do a bar chart of the sampling distribution of the sample means, it looks like this. It's tending towards being symmetrical. And I'm going to talk about that right now. It looks like it's almost what we're going to learn in a few minutes. It's almost normal. So let's go back and see what this means. Let's talk about that now. So what I want to talk about now is what I was just mentioning when I showed you that those bar charts, was something called the central limit theorem. And this is the last thing we're going to talk about before we get into hypothesis testing. The central limit theorem says, and this is very, very important, if all samples of a particular size are selected from any population, the sampling distribution of the sample mean is approximately a normal distribution, and that approximation improves with larger samples. Now, a couple things to be more specific. If the population that you select the sample from is normal, the distribution of sample means will be normal regardless of the sample size. If it's not normal but symmetrical, then it doesn't take a very large sample in order for the distribution of sample means to be normal. But even if it's not symmetrical, even if it's a weird looking distribution, for sample sizes that get larger and larger, the distribution of sample means tend towards a normal distribution. Here's an example of that. So here we have 4 different populations. Look at the shapes of those populations, and look at when we only go to a sample size of 2, look at how this is starting to get close to symmetrical. And for sample sizes of 6, it's getting better and better. And for sample sizes of 30, look at it. We got almost a perfectly symmetrical normal distribution. And the other thing to note is that look at the dispersion when n is 6, and as I mentioned before, as n gets bigger and bigger, the standard deviation gets smaller and smaller. This curve gets tighter and tighter so that we have less dispersion in the curve. So I'm going to go back now and look at what we looked at just a minute ago. And so we had samples of size 2, and we had a distribution that looked like this, the population distribution. But look at, for samples of size 2, how this is starting to get closer and closer to a normal distribution. So even for this small sample, now if we were to take samples of size 3 or 4, this approximation would get better and better. This would get more and more symmetrical as the sample size increases. All right, let me introduce a topic, the standard normal probability distribution, because we're going to use this quite a bit in hypothesis testing. The standard normal distribution is a normal distribution. I assume that most of you are at least familiar with the normal distribution. It's a bell-shaped curve, symmetrical about the mean. But in the standard normal distribution, the mean is 0 and the standard deviation is 1. And this is normally called the z distribution. And the formula for that is that z is equal to x minus mu divided by the standard deviation. So this is the population mean. This is the value of your random variable, whatever the random variable is. And remember when we talked about sampling error, if this difference between the value from the sample and the population parameter is, if that sampling error or if that error is bigger, then z gets bigger and bigger. And as z gets bigger and bigger, then that's more unlikely to happen. It's not expected that you would get large values of z. So small values of z, somewhere around 0, no problem. But if z gets too big or too small, that's an indication that there's a larger sampling error. Okay, here's a picture of the standard normal distribution. You can see the mean is 0, and you can see that in a standard normal distribution, about 68% of the random variables will fall within one standard deviation of the mean, which means between z equal -1 and z equal +1. For z values between -2 and +2, you're going to get about 95% of the values. And for z values between -3 and +3, you're going to get about 99%. So it's highly unlikely that you would ever get a z value bigger than 3 or smaller than a -3. And we're going to use that understanding of that, how unlikely it is that you can get large z values or small z values. When I say small, I mean in the negative direction, like smaller than -3. It's unlikely that those z values can happen. So we're going to use that when we do hypothesis testing, that understanding. Okay, now we're ready to start talking about hypothesis testing. We've got the basis for all of it. We talked about sampling. We talked about the distribution of sample means. We talked about sampling error. We talked about the very important central limit theorem. And the reason the central limit theorem was so important was it told us that the distribution of sample means is approximately normal. And what we just learned about the normal distribution is we can make statements about the chances that z values will be large or small, so we can use the fact that the distribution of sample means is approximately normal to do hypothesis testing. So let's define what hypothesis testing is. A hypothesis is a statement about the value of a population parameter, for example, the mean or the standard deviation. And we want to make that statement for the purpose of determining whether we believe that statement to be true or not true. So what we're going to do is we're going to try to reach this conclusion based on taking a sample and determining whether or not, based on that sample, that our hypothesis is reasonable or not. There's 5 steps in hypothesis testing. The first is to state the null and alternate hypothesis, which we're going to talk about in just a minute. The second is to select a level of significance. Now, a level of significance, and I'm going to get into this more later, is a risk that you're willing to take of creating an error, of making a mistake in your hypothesis test and reaching a conclusion. I hope you understand that there is always a risk. If you go into a population and take a sample, there's always a risk that that sample is not representative of the population and that you could actually, based on that sample, arrive at an incorrect conclusion. The level of significance, also called alpha, is the risk that we are willing to take for that to happen, and I'm going to talk more about that in just a minute. The third step is to identify the test statistic. The test statistic is a number, a value that we calculate based on the sample data. The fourth step is to formulate a decision rule. The decision rule is what we will use to determine whether or not the hypothesis that we're testing is reasonable. And it's going to be based on this willingness to take a risk that I talked about in Step 2, how willing are we to make a mistake? And that will help us. It's not the only thing that will be used to determine decision rule, but it's one of the things that we'll use to determine decision rule. And then the last step is to actually, based on that test statistic and the decision rule, to actually arrive at a decision. Okay, first step was to create a null and alternate hypothesis. The null hypothesis is a statement about the value of a population parameter developed for the purpose of testing some data. The alternate hypothesis is a statement that based on the data that we will use to either prove or disprove the null hypothesis. So here's some important things. These are really important things to remember about the alternate and null hypothesis. The null hypothesis and the alternate hypothesis are mutually exclusive, which means there's no intersection. There can't be something that's in both, and they're collectively exhaustive, which means they encompass all possible outcomes. Nothing's left out. The null hypothesis is always presumed to be true at the onset of the test. We use the H sub O notation for the null hypothesis, H sub 1 for the alternate. And based on the sample, we're going to either reject the null hypothesis, or if we don't have enough evidence to reject it, we're not going to necessarily say that the null hypothesis is true. It only means that there wasn't sufficient evidence to reject it. Let me expand on that just a little bit. Let's suppose that the mean of a population is 10. And we go in and we take a sample, and that sample mean is 9.9. That's close. So our conclusion then would be that based on that sample, that 9.9 is close enough to 10 that we can't say that 10 is not reasonable. But just because, I've talked to you about this before. When you go in and sample into a population and take samples, you get lots of different sample means, many of which are not equal to the population mean, but should be close. So if that sample mean is close to the population mean, or what we think the population mean is, we're not able to say that it's not 10. So we get a sample mean of 9.9. We can't say it's not 10. We get a sample mean of 9.7. We can't say it's not 10. But if we get a sample mean of 4.1, we can probably say it's not 10. So we either reject the null hypothesis and conclude that it's not true, or we say there's not enough evidence based on the sample to conclude that it's not true. We really can't say it's true. We can just say there's not enough evidence to say it's not true. Really, really important. This mistake's made all the time. The equal sign must always be part of the alternate, the equal sign must always be part of the null hypothesis. Always. Never in the alternate hypothesis. Okay, so let's look at the art of establishing a null and alternate hypothesis. What you have to do is you have to look into your situation and look for keywords. So for example, the keyword improved. Improved would be basically saying made better. Now made better could be made bigger or smaller. If we're talking about profit, improved would be better. If we're talking about quality or defects, improved would be less than. So improved could be greater than or could be less than. Greater than and less than must always be in the alternate hypothesis. Remember, the equal must always be in the null hypothesis. Different from means not equal. Could be bigger, could be smaller, not equal. Has changed means not equal. So over here are some keywords. And you can look at the symbol that we're interested in. So smaller means less than, larger, greater than, no more than means less than or equal to, which must be in the null hypothesis. At least means greater than or equal to, must be in the null hypothesis. Has increased is greater than, must be in the alternate hypothesis. Just remember, the equal sign must always be in the null hypothesis. Okay, test statistic versus critical value. The test statistic is the value that we have determined from the sample. And we're going to use that to try to reach our conclusion about whether or not we should reject the null hypothesis. The critical value is the dividing point between the region where the null hypothesis is rejected and the region where we don't have enough evidence to reject it. So let's look at that a little bit further. So we're going to look at that a little bit further. What I'm going to talk about now is test statistics. If the population that we select the sample from is normal, then the sampling distribution is also normal. We've already talked about that. Or if we have a large enough sample, then we can assume that the distribution of sample means is normal, and we arrive at this test statistic. So this is a z-value that we would calculate. This is known as the test statistic, and notice that it's based on a comparison of the sample mean and the population mean. Now, this numerator here, that's the sampling error. If that sampling error is real large, then, and you know, we already said it's unlikely for the sampling error to be large. If that error is large, then that's an indication to us that our thoughts about what the population mean are probably not accurate. So if our z-value is too big or too small, bigger than 3 or smaller than -3 or whatever value we come up with, if that value of z gets too big or too small, then we're going to conclude that based on this sample, based on this x bar here, that this, what we thought the population mean was, is probably not true. Now, if the population is not normal, we would use a t-distribution, and it's slightly different. It's almost the same, but it's basically the same concept. Okay, so let's look at some hypothesis testing here for a particular case where we're looking at testing the hypothesis on the mean of a single population. Now, let me start by saying that we can test hypothesis on things other than the mean, and we can test hypothesis on more than one population. So we can compare the means of two populations, for example. And depending on what hypothesis we're testing and how many populations we're looking at, the test statistic will change. So those test statistics we looked at just a minute ago, these were specific to testing the hypothesis, testing a hypothesis on the mean of a single population. Both of those, mean of a single population. So let me talk about a couple things that are really important here. Number one, this is really important. It's very easy. If the null hypothesis is greater than, the critical region will be greater than, whether it's a z or a t. If the alternate hypothesis is less than, the critical region will be less than. If the alternate hypothesis is not equal to, then the critical region will be on both sides, greater than and less than. Note in every case that the equal sign is in the null hypothesis. These are the test statistics down here. This is a test statistic for t when the population distribution is not, the population that we took the sample from is not normal. And this is for z when the population was normal. So those are the test statistics, and these are the critical regions. One more time. Once you know the direction of the alternate hypothesis, you know the direction of the critical region. Okay, so this is just a follow-up. If the alternate hypothesis is less than, then the critical region will be on the left tail. If it's greater than, it'll be on the right tail. If the alternate hypothesis is not equal to, it'll be in both the right and left tail. You can be too big or too small if it's a two-tailed test. Now this critical region, I mentioned it slightly earlier. This is based on alpha, the level of significance that we're willing, or the level of significance that we determine at the beginning of the hypothesis test, and our willingness to risk making a mistake. So I'll show you later how to calculate that. We'll get that in a little while. Okay, decisions and errors in hypothesis testing. I told you a few minutes ago that as long as you're sampling, there's always a risk of an error. Let's look at what can happen. If the null hypothesis that you've created is in fact true, and you do not reject, remember I didn't say accept, I said we don't have enough evidence to reject. If it's true and we don't reject, that obviously is a correct decision. But if we do reject and it's true, that means we got a bad sample, we got one of those weird samples, and we created an error, and that's called a type 1 error. If the null hypothesis is false and we do not reject, that's a type 2 error. If it's false and we reject, that is obviously a correct decision. Okay, now let me talk to you about the relationship between a type 1 error and alpha. I told you at the beginning when we started talking about hypothesis testing that you have to choose a value for alpha, the level of significance. Typical values are 0.01, 0.05, 0.10, and so on. Alpha, the level of significance, is the risk that you're willing to take of creating a type 1 error. So if you say, I'm going to set my level of significance to be 0.05, what you are saying is, I am willing to take the chance that I will conclude that the null hypothesis is not true when in fact it is true. I'm willing to take that risk at the 5% level. I'm willing to take a chance of that happening 5 out of every 100 times. Another way of saying that is there are 5 out of 100 samples out there in that population. If I go look at 100 samples in that population, there are 5 of them that would tell me to reject when I really shouldn't reject. That's a type 1 error, and when you establish alpha at the onset of your hypothesis test, that's the risk of a type 1 error that you are willing to accept when you start the test.